This video looks at the requirements for NMR, nuclear magnetic resonance spectroscopy for A2. So this is the first video of two videos, and we're going to look first of all at what's called low resolution NMR. So if we look very quickly at what happens with regards to NMR, how it actually works. So just a very brief introduction. So NMR is a high-tech analytical technique. It allows us in chemistry to help to deduce the structures of molecules, particularly in A-level chemistry we're looking at organic molecules. And it allows us to do that by detecting what we call the environments of hydrogen atoms. If you think about pretty much every organic molecule that you've looked at so far, it has some hydrogen atoms in it. And if we can detect the environment that those hydrogen atoms are in, so are they in a CH3 or an OH or a COOH or a CHO, then we can start building up a picture of the structure of that particular molecule. So this is the piece of equipment that we use. I'm not going to talk in really very much detail about this because in essence you don't really need to know very much about it, but some people will be interested in sometimes understanding the principles behind the actual spectroscopy can help you understand what's going on when you apply or go to apply your knowledge to answer questions. So if we look at it, we have basically got a casing of liquid nitrogen. The purpose of that really is to keep everything cold and act as a sort of a thermal insulator. The reason for that is because we have a very, very strong magnet in the middle called a superconducting magnet. Superconducting magnets essentially are electromagnets which run with zero resistance, and zero resistance only happens at exceptionally low temperatures. And you can see on the board there we have the superconducting electromagnet minus 269 degrees Celsius. That's about 4 Kelvin. So that is an exceptionally low temperature, and that's the temperature you need. That's the critical temperature that you need to get to for a superconducting magnet to actually behave as a superconducting magnet. Okay, and that basically what that does is it gives the magnet, if you like, for want of a better word, superpowers. It makes it an exceptionally strong magnet that you wouldn't get were the temperature to be higher. Okay, you'll see that that's surrounded by liquid helium, and liquid helium is essentially there to keep that magnet at the temperature it needs to be kept at. And that's surrounded by the liquid nitrogen to keep the helium cool. Helium is very expensive, liquid nitrogen not very expensive. So you basically surround the helium to try and stop it from boiling off. It does boil off eventually over a period of time. That just kind of happens, but the liquid nitrogen slows its boil off as best you can. So when we hit these hydrogen atoms with radio frequencies, okay, they will absorb them, and they're absorbed by the sample, and only particular frequencies will get absorbed. And pretty much the key thing is here that we can measure the radio frequencies that are absorbed, and we can correlate the absorption of those frequencies to hydrogen atoms in particular environments. And we get then an NMR spec that looks a bit like the one on the screen now. Now we'll have a look at NMR specs in great detail as we go through this, so don't worry about that rather small one on the screen. So this is kind of essentially what happens when we're talking about nuclear magnetic resonance for hydrogen atoms. Now, remember hydrogen atoms, as you will know from back as far as probably key CH3, hydrogen atoms contain one proton and they contain one electron. So in their nucleus, which is what we're after here, and remember nuclear magnetic resonance, in the nucleus they have one proton, and that proton sits in spin. Okay, and if you think about the proton when it sits in spin, you won't, unless you probably do A-level physics, you won't probably know that a single proton spinning in a nucleus on its own exerts a very small magnetic force. It behaves essentially like a little magnet. And if I then apply an external magnetic field to that, okay, you can see here, all of the little magnets, the little protons within the nucleus of the hydrogens will align with the magnetic field. No different than if you imagine having hundreds of tiny little bar magnets and you apply a magnetic field to those, they will all align with that very strong magnetic field. I can then apply energy to that in sort of in the terms of radio waves, and I can get all of those tiny little bar magnets or the nuclei of the hydrogens to oppose that magnetic field. Then what we can do is we can measure the energy gap between where the protons align with the magnetic field, where they oppose the magnetic field, and we can essentially use that energy gap, okay, to tell us what environment those hydrogen atoms are in. So for example, the energy gap would be different if I had a hydrogen atom in that carboxylic acid group. It would be different again if I have a hydrogen atom in this environment here, primary alcohol group. It will be different again if I have a hydrogen atom just in, let's say, something like ethane. Okay, so it's not quite as simple as I portray it there, but you've got hopefully a bit of an idea of how it happens and what goes on in terms of A level. Now, how do we take measurements then within this actual NMR? Well, everything is measured by what we call a chemical shift value. Now, again, really all you need to know is what the chemical shift value actually is and how you use it to identify hydrogens. You don't need to know how it's worked out or anything like that. And if you think about it, everything's going to have every single different type of proton. So maybe the protons that I spoke about on the right hand side of that screen. Every single proton will have a different chemical shift value. And every chemical shift value is compared to a standard reference. So if you remember when you did electrode potentials, electrochemistry, you compared everything to the standard hydrogen electrode. If you think of something as simple as when you did masses, you compared everything to 1/12 of the mass of a carbon 12 atom. Well, here we compare everything to a compound called TMS, which is tetramethylsilane, and we'll come to that in a little second. And we work out our chemical shift, okay, by comparing the frequency of the TMS absorption minus the frequency of the sample we're looking at over the frequency of the TMS multiplied by 10 to the 6. So you can see these chemical shift values and the energy involved here is extraordinarily small. Okay. Now, that equation that I have on the board now, I wouldn't worry too much about it. You don't need to know it. I just put it in there as a matter of interest. So the units of chemical shift are extremely small. They're in parts per million. Okay? And the chemical shift value that we allocate to TMS, to tetramethylsilane, is 0. So it's our standard. Everything else is compared to it. It's given 0. Okay? And our hydrogen atoms or hydrogen protons, hydrogen nuclei, absorb pretty much within the range of 0 to 12. Okay, so and we get a kind of a graph like this. So if we look here, we've got our TMS here, and then everything else is what we call downfield of TMS. So this particular molecule that we're looking at here, if we just draw it out to remind you, this is butanone. Okay, and you will hopefully by the end of this lesson or by the end of the next lesson, when we look at high resolution NMR, you'll be able to work out what is going on with these peaks. What do these peaks actually tell me? Why are they where they are? How can I use them to work out the structure of, in this case, butanone? Okay, let's look at what we do in order to actually get our readings from the NMR machine. So we've got to take our sample and we've got to dissolve it up into a suitable solvent. And we very often use deuterated trichloromethane. Now, you will frequently in an exam question be asked for a suitable solvent. Just know one. You don't have to know any more than one. Just know this. And this is one, or there'll probably be one in your notes or your textbook. Now, deuterated, for those of you who don't know, deuterium is an isotope of hydrogen. Okay? And it has one proton and it has one neutron in its nucleus. And you might go, why use deuterium? Why not use CHCl3? Why not just use normal trichloromethane? Well, normal trichloromethane has a hydrogen atom in it, okay? And that hydrogen atom has only got one proton in its nucleus. And because of that, it will produce a signal in your NMR trace. And that signal will interfere with the signals produced by your sample. And some of you hopefully now are going, well, why would deuterium not do the same? It's still hydrogen. Well, for the simple reason that NMR machines are only sensitive to atoms which have uneven or odd numbers of particles in their nucleus. Deuterium, which is an isotope of hydrogen, has 2 particles in its nucleus and therefore will not produce a signal in the NMR. So that's the reason why we would use a deuterated trichloromethane. Okay, so TMS then is used as our standard. Everything is compared to TMS. Okay, and that is tetramethylsilane. And if you think about tetramethylsilane, it's a silicon in the middle surrounded by 4 CH3 groups. And we'll look at the reasons why tetramethylsilane makes such a good standard. So that's our internal reference. Okay, and the NMR absorptions of all of our hydrogens that we look at, it says carbon-13 there as well, which is true, but we don't study that at A level, so we're going to ignore that. Okay, everything is measured compared to the hydrogens that are in TMS. Okay, now why is TMS such a good internal reference? Well, first of all, it's got 12 hydrogens or 12 protons per molecule, so it's got loads of hydrogens. Okay, it gives you a really strong signal. The second thing is, this is really important, it only gives you one signal. All of those hydrogens are in the same environment. They're what we call chemically equivalent. So if you look at every single hydrogen in here, okay, it's attached to a carbon, which is attached to a silicon, which is attached to 3 other methyl groups. And that's true for every single hydrogen. So not only do we have a strong signal, but we have a really sharp signal, just one signal. And that's what you want whenever you're using it as a reference. You can't have a reference that produces several signals. It absorbs at a very high frequency, so that's good because it absorbs outside of the frequencies that your sample will be absorbing, so you don't get the signal for your TMS integrated into your sample's peaks, okay, or your sample signals. And the other thing is it's inert, so it doesn't react with whatever you're going to put into your NMR machine to actually analyse. So what does NMR actually tell us? Well, first of all, as I've already said, it detects only atoms which have odd mass numbers. Now, that's lots of atoms, but the good news for you is the only one that you have to study at A level is what we call proton NMR. So you will only be asked to study or examine NMR traces and identify hydrogens or protons. Okay, it differentiates groups of hydrogen atoms, okay, within different molecules. So, for example, things like I have on the board now, that molecule there, which is methylpentane. Okay, NMR machines, you can see here we have a CH3 there, a CH3 there, and a CH3 there. These 2 CH3s in the red are in absolutely identical environments. If you look at it, they're attached to a CH2, which is attached to a CH, which is attached to a CH3, and if I go the other way, exactly the same sequence of atoms occurs. So those 2 CH3s are in the same environment. This CH3 here is in a different environment. And NMR machines have the ability to detect those being in different environments and allow us to know that yes, we have 3 CH3s in here, but 2 of them are in the same environment. One of them is in a different environment. So it's a really sensitive and useful piece of equipment. So if we look at that molecule there, if I maybe just draw this out in a little bit more detail at the minute because we're just kind of getting used to this. Okay, so that CH3 and that CH3 are in the same environment. So I will get one, what we call signal there. This CH2 and this CH2, exactly the same environment also, that will give me a second signal. This CH here is in its own environment, that will give me a third signal. And this CH3 here is in a different environment, the other CH3s, that will give me a fourth signal. So that's the first thing that we can work out with an NMR is the number of signals tells me the number of different environments. So in this particular molecule, I will get 4 different signals, and that will tell me I have hydrogens in 4 different environments. Now, the next thing that it can tell us is for proton NMR, it can count the number of hydrogens in each of those environments. Okay? It gives us a ratio of the hydrogen atoms in those environments. So for example here, back to the molecule that we just studied, we already established that we're going to get 4 signals, so we know we have 4 environments. If we are able to measure the area under the peaks, okay, which the computer will do for you, by the way, you won't be asked to do that, okay, you will get an arrangement of a 6:4:3:1. And that tells me in one of my environments, so A, obviously, I have 6 protons. In another environment, which is of course B, I have 4 protons. In a next environment, which is going to be D, I have 3 protons, and then there's another environment in there, which is 1 proton. So far we know that NMR can tell us how many different environments, hydrogen environments, do we have within a molecule. Now it tells us how many protons are in each of those environments, or how many hydrogens are in those environments. This is called the integration trace, or the integration lines, okay? So it'll be called something about integration, or integrated spectrum, or integration trace, okay? So just be aware of that word meaning exactly what I've just said. So maybe if we look at this one here, you can see we have, this is a butanone, by the way. Drew it out earlier. I'll draw it out again just so we can see. Sometimes, guys, if you're struggling with these, make sure you draw the molecule out. If they ask you how many environments there is, how many signals there should be, always draw it out. Don't just, unless you're exceptionally comfortable with doing it. So here we can see there's a CH3 on the left and a CH3 on the right. They're in different environments because this CH3 is attached to a CH2, this CH3 is attached to a C00. So that's a different environment. So there's A and B environments, if you like, and then this CH2 is in its own environment as well. We're going to get a peak integration trace, or an integrated spectrum, of a 3, a 2, and a 3 here. Okay, so that is as much as we can tell at the minute, and that's the sort of thing that we would get there. Okay, and if we were to put the integration trace on this, or the integrated spectrum on this, you get something like that, and that'll be put onto yours in an exam. And how you prove it is you just simply measure from there to there, and when you do that, that'll come out as a 3 to 2 to 3. Okay, and that will tell you that you've 3 environments, because you've got 3 signals, or 3 peaks, and you've got 3 protons in one, 2 in another, and 3 in a third. Now, similar hydrogen groups in different molecules can be differentiated by their different chemical shift values. So if I go back to this, you'll see I had here 2 CH3s, but they are at different chemical shifts. So this is very useful, because it would be quite ridiculous if every CH3 gave us the same chemical shift value, because then they would just all overlap. So what happens there? Well, the closer that those hydrogen atoms are to an electronegative atom, the higher the chemical shift. Okay? So if I took the molecule the butanone that we had on the previous slide, hopefully you guys can see that this environment here is closest to that oxygen, whereas this CH3 environment here is furthest away. Okay? Now, we can hopefully now attribute the CH3 groups to where they are on the chemical shift trace. So here, this one here is closest to the electronegative oxygen, so it is furthest downfield, or has the highest chemical shift value. This CH3 here is furthest away from it, okay? So it has the lowest chemical shift, and the CH2 is in the middle. Now the reason for this, we don't need to get into too much detail here, but the reason for this is pretty straightforward. The electronegative oxygen atom is able to de-shield the electrons from around that green hydrogen environment. In other words, it pulls them away. And that means that lower frequencies are required to make those protons oppose the magnetic field, the external magnetic field. And that means that our chemical shift becomes higher. Okay? So basically, for A level, your rule of thumb is the closer the protons are to electronegative atoms, the further downfield they are, okay? You don't really need to know much more than that. And you just say that that is because they are de-shielded, okay? Whereas the CH3 here in the red is more shielded or less de-shielded. And you will see, you'll get a table in your exam, which might be similar or slightly different to this one, where you're able to identify now particular protons with their chemical shifts. You will see here the proton in a carboxylic acid group has the highest chemical shift, because you can see it's right beside two very electronegative oxygen atoms. So it is highly de-shielded, okay? So why do all hydrogen in a molecule not absorb in the same chemical shift? Well, that's kind of what I've already said. It depends on the electron density around the proton. And the closer that proton is to an electronegative group in the molecule, the lower that electron density around the hydrogen will be, because the electronegative atom is withdrawing that away. So hydrogen is what we call de-shielded, okay? And it needs a lower frequency for absorption. And that lower frequency is equivalent to a higher chemical shift, or a further downfield chemical shift. OH absorptions then you need to know about. They're a little bit odd. Okay, and again, we're not going to go into a whole load of detail here. Okay, but the chemical shifts of these vary lots. Okay, now at A level they are fairly tidied up for you, so it's not too bad. But it does depend on what solvent they're in, how pure it is, how much water impurities are in with them. Okay, but we can identify them relatively easily. Okay, and sometimes this pops up. So if I have, let's say, ethanol, and ethanol has an OH group, okay? Now the thing about OHs, right, is they're what we call labile protons. Now I'm not going to confuse you too much with what a labile proton is, but basically it's a proton that can swap with other protons around it, okay? This very electronegative oxygen here, okay, makes this very delta positive, and it weakens this bond because the electrons lie close to the oxygen. So basically this proton here can pop on and off really, really quickly with others around. So if I pop this into some heavy water, deuterium, okay, oxide or deuterated water, okay, which has D2O, this D can swap with that hydrogen really quickly, and it does it quicker than the NMR machine can pick up. So what happens then is that peak, that OH peak, disappears, okay, for the simple reason that the hydrogen on the ethanol gets swapped with the deuterium atom, which, remember from earlier, has an even number of particles in the nucleus, and because of that it doesn't give a signal. So if chemists are unsure if there's an OH group present or not, they will add some deuterium oxide to it, run the trace again. If the peak disappears, then that peak was because of the presence of an OH. Okay. Okay, so that's all the sort of background done, guys, and we're now going to have a look at examples of how do we actually interpret these NMR spectra, which is what you're going to have to do in an exam primarily. So we're going to look at three molecules here. You're going to work out, or we'll sort of work them out together, but if you think you're capable of doing this, you can just crack on and do it yourself. We're going to look at how many different hydrogen groups there are, so how many different signals would we get, and what will the ratio under those peaks actually be. So you maybe want to pause the video now, draw the molecules out would be my advice, and do fill in the table. I'll go through them very quickly here. They're three very simple molecules, so it shouldn't hopefully be too much hassle for us. So I'm going to do this now if you want to pause the video. So in the first one, we're only going to have two environments. That CH3 and that CH3 are the same, and that CH2 is on its own. The next one we have three. That CH3, CH2 and the CH2 are all in different environments. And here I have a CH3 here and here, but they are very different environments. And then we have a CH2. So the number of different hydrogen groups correlates to the number of signals. The ratio for the first one, I have 2 CH3 groups and 1 CH2 group, so that's 6 to 2 or 3 to 1. And the next one, I have a CH3, a CH2 and a CH. Okay, so that is actually not right. It's a 3 to 2 to 1. Okay, and on the next one, I have a CH3, a CH2 and a CH3, so that's a 3 2 3. Okay, so there are some more complicated ones. Well, they're not that bad actually, down below. I'm not going to go through all of these. If you want to pause the video yourself, guys, draw the molecules out, okay, and then I will pop the answers up. So pause the video now if you want to. Okay, so we've moved on to the next question. You probably want to pause the video again, have a look at that one. You should be able to work this one out now. So if you pause the video and then I'll go through it. So if we look at A will give us 3 signals. So 1, 2, 3. So it can't be A because there's 4 signals on the trace. This is a really simple example, by the way. If we look at B gives us 1, 2, 3, 4 signals. So it could be B, yeah. If we look at C, and I'll draw it out because there's a little branch here, okay, so we go CH3, CH3 here again, and then we have an aldehyde group. Okay, so that CH3 and that CH3, if you go through the molecule, are in the same environment, so that's just one signal, those. There's a CH2 there, or sorry, a CH there, so there's number 2 environment there, and then we have this single hydrogen zone. That's number 3 environment, so that C molecule would only give us 3 peaks. So the answer has to be 4 because it doesn't really matter about the ratio. Okay, it's just a simple fact that B is the only one that gives us 4 peaks. Okay, have a look at this question here. See how you go. Pause the video. I will go over it. So I'm just drawing the molecules out first, and C is methyl propanoate. Okay, all right, so let's have a look first of all at which one of these is which. So if we look at A is going to give us 2 peaks. There's a hydrogen environment there and there's a hydrogen environment there. So A could only be, or sorry, methyl methanoate could either be A or C. Now the ratio is going to be a 1 to 3 here, so that one has to be C. Methyl methanoate has to be C. That's a 1 to 3 ratio. Okay, and we can see our 1 is well downfield because it's near these oxygens. If we go to number 2, again, or the methyl ethanoate is going to have 2 peaks here and here, 2 CH3 groups, different environments, but their 2 CH3 groups are going to be in a 1 to 1 ratio. Has to be A. And then if we go down to the final one, which is methyl propanoate, okay, we have a CH3, CH2, CH3, so it's 3 peaks, so it has to be B, okay, and they are in a ratio of 3 to 2 to 3, so therefore it is absolutely B. I just skip through. Okay guys, so hopefully we've done a few examples there. You have lots of past paper question examples and questions in your question book if you want to have a go at those and check the answers against those. Alright, hopefully that helps with low res NMR, high resolution NMR. I'll do a separate video on. Make sure you do that. Okay, I'll probably look at the low res video and then look at the high resolution video really quite quickly after it. Okay.